Okay, in this section, we review some basic concepts and invariant use in our algorithms. Okay, so our algorithm, not our, just that's too presumptive. Just the author, the algorithm in this paper follows the footsteps of some previous works and is designed with the primary goal of restoring the invariant 2.2 we introduced in the previous video. And after each update operation, the invariant is crucial for maintaining the structure and efficiency of the dynamic connectivity data structure. In the following sections, we will outline the key components of the algorithm and the primitive data structure operation that support it, as detailed in the following slides. Okay, this is the data structure. Let's bring out the laser pointer here. This is the hierarchy forest which we built in the previous section. So we know that V1 hat means the connected component of G2, right? And V2 hat means the connected component in G3. All right. So this is basically a tree representation of the hierarchy. So the hierarchy contains all the G hat of G hat I, which is defined here. If you still remember here, so the G hat I, which is defined to be V hat I and E hat I. All right. So the hierarchy includes all the G hat I, and we would like to represent it as a tree for more structural visualization in this algorithm. Okay, so this is the graph that was used in the description of the paper, and we already introduced it in the previous section using the PowerPoint slides to explain some whatever G hat, V hat, E, what is E hat. Okay. All right. So as we know, there are three operations: insertion, deletion, and connectivity query. Okay, so for insertion, so they insert UV, meaning that we want to insert an edge connecting U and V. So this operation is to add an edge to our data structure, right? So we're starting by setting the depth of the edge to, of course, 1. And this is the initial step for all insertion. And next, we need to check if the edge connecting two separate components in the graph. Okay, so how should we check it? We just make a connectivity query over the maximum spanning tree, because the maximum spanning tree or maximum spanning forest will answer whether these two UV are in separate or not, or are in separate components or not. Okay. So if the edge does connect two distinct components, we then proceed to access the edge root, which is the root at the hierarchy, okay, of U and V, and we merge merge them, and we just insert E as a one witness edge. Otherwise, if U and V are not in distinct components, but they are in the same component, we then just insert the edge as a one non-witness edge. Non-witness just means that it does not belong to the maximum spanning forest. Okay, that's quite simple. So for deletion, which is the main focus of our algorithm, algorithm. So in the deletion operation, we start by removing the edge E from the hierarchy forest edge and node and node and let's say the depth is I, okay? Let's say the depth of the edge we would like to remove is I here. So the complexity of a deletion process really depends on whether the edge E is an eyewitness or an eye non-witness edge. It just means that whether these edge belongs to the spanning tree or not. Okay. So if E is an eye non-witness, its removal does not affect the connectivity of the eye component, which we already know, and thus the deletion process is straightforward and complete. Okay. So, however, if E is an eyewitness edge, its removal could be potentially split an eye component, necessitating or requires a search for a replacement edge for these for the same depths to maintain the connectivity. So this initial step sets the stage for a more complex process when dealing with eyewitness edge, as we aim to preserve the maximum spanning forest property of invariant 2.2. Sorry. So let's take this graph for example, more concrete, more easy to understand. So we would like to delete this edge. Okay. So we first make an query, all right? So the query responded, okay, this edge does connect two connected component, separate distinct connected component, this one and this one, okay? All right. And we noticed that these two connected component at in V2 hat along with others connected components form a larger a single I component. This basically means the tree relationship. These two, along with others, form a single I component here, which is ui minus 1, and also it is vi minus 1. All right. So after we remove it, but there's no replacement. Remember that a replacement needs to be of the same depth of I, okay? Same depth. But there are no replacement here, alright? So, in this scenario, in this circumstance, we will have a split of ui minus 1, which is vi minus 1. Okay, then we will revisit this example in the later page. Don't worry if you miss here, but we will catch up with the idea very soon. Okay, but how can we check if the above holds? What is the above? The above is that whether there is a replacement. So how can we check whether a replacement edge exists? All right. So there are two steps here. The first one is to establish CU and CV. And CU-CV implicitly split the I component, which is this one, I component, into CU and CV in fi hat, and fi hat basically mean remember gi hat is vi hat, and vi hat. But if we say fi hat, it just consider the edges in the spanning tree. All right. So we this first step is to establish cu and cv to split the I component, and we want to this implicitly split implicitly split, not explicitly split. So, and the second step is to find the replacement edge to reconnect cu and cv. All right, quite confusing, is it? That's right. I really spent a lot of time uh, digging into the materials in Section 3. But whatever, I hope it is more clear if I explain it to you this way. Okay, so when an eyewitness edge is deleted, we must carefully assess whether its removal split an I component into two. All right, and we can check by first splitting the I component into two new kinetic components, Cu and Cv. Right. And we find a replacement to reconnect these two. But how? The step one, let's elaborate it further. So to identify the two components, Cu and Cv, resulting from the deletion of an edge, we initiate two parallel graph searches from node ui and vi parallelly. So these search aims to explore all mark I plus 1 components to identify Cu and Cv, and gradually building up these components Cu and Cv, the process continues until one of the components is fully scanned. Why we only need one to be fully scanned? Because we know that ui minus 1, which is these small blue connected components, is going to be split into two. So or if we already know the weight of one, we know the weight of the others. Right. And the weight, by definition, is the number of vertices in this connected component. So this process continues until one is fully scanned, okay? So this allows us to determine the weight of both components. And without loss of generosity, we just assume that Cu has a lighter weight than Cv. So by the second property of invariant 2.2, we have Cu must be smaller than, of course, half of the weight of ui minus 1, because if you split into two and the lighter weight, the smaller part must have a weight smaller than the half, and we apply the invariant 2.2, the second property, which is the weight property, to this weight, then we have n over 2 to the power of I. Okay. So following the establishment of components of Cu and Cv, the next step involves promoting eyewitness edge that are in contact with nodes within Cu. Remember, Cu is the smaller component in the split. Alright. So these actions facilitate the merging of all I plus 1 components. And the merged components we will denote it by UI merge. We'll have UI minus 1 as its parent. This kind of words is very ambiguous, and we will look at a very concrete example to explain it. So let's see these examples. So at first, so after identify two components CU and CV, all right, CU and CV, that is that's just a partition of UI minus 1, all right. Then we will merge, and we assume that CU has fewer lighter weight, which it means it has a fewer number of vertices. So we just merge all the connected component in GI hat, right? Then if no replacement edge is found, then CU, CV are just two actual connected component in the light blue, and then we can just split it into two, if that is the case. All right. I think it's better to just look at an example here. All right. So for the same graph, if we want to delete the edge connecting V3 and V5, okay, V3 and V5, which is this edge, okay. This edge we want to delete it. Okay, after the deletion, we are going to build CU and CV. So CU and CV, how are we going to build them? So let's see. So execute parallel graph search from UI and VI and find out let's see, all the edges in EI, EFI. FI is the EI intersection with the spanning tree, right? So we in parallel, after the deletion, V3, V5 is deleted. So we're starting from V3 and V5, and we want to find out all the edges with depth 2, which is this one and this one. So V3 we can find out 1, 2, 3, and there's no more. And V5 similarly, what are vertices that incident to it connected by list 2 is 1, 2, 3, 4. So this is smaller. It only has three vertices, and this one is larger. So this is one is CU, and this one is CV. Okay. The key point is that starting from U and V and find out all the incident vertices to U and V. The only constraint is that it has to either already within the connected component or connected through a depth of I. In this case, I is 2, so we only consider these two edges. All right. This is 1, so we are not considering 1 here. All right. So what's the next step? The next step is merge all the connected components within the smaller CU. Okay, so let's merge. So we already know that CU is this one and CV is this one. So we merge. We can see in this slide there are two separate connected components, and in this slide the two connected components merge into become one connected component. And after merging, we need to promote here. We need to promote edge promotion. All the edges touching nodes in CU. Okay, within CU. So we know that here CU is this 3, right? So all the edges in the spanning tree touching CU is only this one, right? So we need to promote. Promoting means that increment the depth of the edge. So the depth uh, was transitioned from 2 and was promoted to 3. So merging and plus promotion. It only happens within CU. All right. And next step is to find the replacement edge. Okay. So the replacement edge need to have the same weight too. So let's see whether there exists an edge that is 2. So it happened here. It happened to be this one connecting V3 and V4. It is a replacement. All right. So that's it. And when we are updating our graph, we can we also updating the data structure hierarchy tree here. That's, for example, when we are merging two connected components, we are merging the connected component represented in the hierarchy tree here. All right. And another example. So after deleting, if in next step we want to delete V4 and V5, which is let's see. All right. Initially there exist V4 and V5. I maybe just deleted this the initial slide. And if we want to delete V4 and V5, and by definition, we have to split the edge node in V2 hat. Why? Because V2 hat, as we know, what is V2 hat? V2 hat is the connected component of G3. G3 is all the edges with depth at least 3, right? So if we remove V4, V5, then V4 and V5 are not connected by any edges. So they are not in the connected components as they are not connected. All right. So by definition, we need to split the edge node. Edge node simply means the node in the hierarchy tree. Okay. So here you find in the slide there is only one edge node here, and in next slide the edge node connecting 4 and edge node connecting 5 became separate. All right. And after transforming it into a graph that is conforming to the definition, we just use the same tricks, same heuristic, and we find CU and CV. Again, don't forget that we were going to delete V4, V5. So U is V4, V is V5. So we want to find out CU and CV. So what is CU? CU has one connected with the edge of depth 2, 2, 3, 4, and V5 has 1, 2, 3. So in this case, CU is this one, and CV is this one. Okay, it has 4 vertices. So V5, V6, V7 is the smaller weight component, which is CU. So we merge it and promote the edge within it. Okay, merge and promote, right? So we just merge these two light blue connected components and promote the spanning tree edge within the connected component. So don't forget to update. Don't forget to update the hierarchy tree correspondingly. All right. But here, after merging, initially V4 and V5 was connected by an edge of 3. But here, after merging, we cannot find any edges that is of a depth of 3. So in this case, which resort to our initial example, we have to split. We have to look to its parent, look to the upper hierarchy, and split the connected component in the higher hierarchy. So we cannot find replacement at the lower hierarchy at depth 2. Then we need to split the component at a higher hierarchy. So we just split, since we already know CU and CV. So we split according to CU and CV, and we also update the hierarchy tree accordingly. And in this scenario, we can find the replacement edge 1 as a witness edge. A witness edge is just basically an edge in the maximum spanning tree. But here, because we are in V1, so the edge connecting two connected components is smaller than 2. It's 1. All right. Oh, that's quite easy, but also complicated based on all the definition and notation and some inconsistency between the VI hat and the GI plus 1. And in next video, we will just scrutinize all the textual description of this algorithm, and that's it.